Half-metals are a special class of materials that exhibit metallic behavior for electrons of one spin orientation while acting as insulators or semiconductors for electrons of the opposite spin. In other words, they conduct electricity through only one spin channel, either spin up or spin down, resulting in 100% spin polarization at the Fermi level. This unique electronic structure arises from the interplay between the material's atomic composition, crystal symmetry, and magnetic order. The concept of half-metallicity was first proposed in 1983 for the compound nickel-manganese antimonide, NiMnSp, a so-called half-Herzler alloy. Since then, half-metals have become central to the field of spintronics, where the spin of electrons, rather than their charge alone, is used to process and store information. In a typical half-metal, the density of electronic states at the Fermi energy differs completely between the two spin channels. For the spin channel corresponding to metallic behavior, there are available states for electrons to occupy and move freely, giving rise to high conductivity. In contrast, for the opposite spin direction, a band gap exists similar to that in semiconductors, preventing electrical conduction. This asymmetry leads to full spin polarization of the conduction electrons, which can be exploited to generate spin-polarized currents with exceptional stability and efficiency. Because of these properties, half-metals play a vital role in modern spintronic devices. They are used in magnetic tunnel junctions, spin valves, and magnetic random access memory, MRAM, where they serve as spin injectors or spin filters to control electron spin transport. These applications are crucial for the development of non-volatile memory devices, logic circuits, and next-generation computing technologies that are faster and more energy efficient than traditional charge-based electronics. Half-metals are also being explored in spin transistors, where their fully spin-polarized current can be used to modulate device conductivity through magnetic or electric control, and in spin-based quantum computing architectures that rely on manipulating single electron spins. In addition to electronics, half-metals are also of interest in the field of catalysis and magnetic sensors. Their spin-selective conduction makes them suitable for use in spin-dependent electrochemical reactions and in high-sensitivity magnetic field detectors. Furthermore, the combination of metallic and insulating characteristics within one material offers new design possibilities for hybrid nanostructures and multifunctional heterojunctions, which can integrate magnetic, electronic, and optical functionalities in a single device. Several families of materials exhibit half-metallic behavior. The most prominent examples include the Herzler alloys, such as NiMnSp and Co2Mnc, which are well known for their robust spin polarization and tunable magnetic properties. Manganite perovskites like La0.7 Sr0.3 also display half-metallicity at low temperatures due to strong exchange coupling between manganese ions and oxygen atoms. Chromium dioxide, Cro2, is another well-established half-metal, used experimentally as a spin source in magnetic tunnel junctions. More recently, researchers have predicted and observed half-metallic properties in various oxides, sulfides, and even two-dimensional materials like vanadium-doped graphene and transition metal dichalcogenides, suggesting that half-metallicity can emerge in a wide range of structural frameworks and chemical systems. Overall, half-metals represent a key bridge between magnetism and electronics. Their perfect spin polarization makes them ideal candidates for controlling spin transport at the nanoscale, paving the way for highly efficient, miniaturized, and quantum-ready electronic technologies. As material synthesis and computational design methods continue to advance, new classes of half-metallic compounds are likely to appear, further expanding the technological potential of this fascinating group of materials.